Hi everyone, welcome to today's video on how binaries are loaded and executed on Linux machines. However, the similar concepts can be extended for Windows system with P binaries. Today we'll explore the entire process from loading to execution and dive into system calls using strace. By the end of this video, you'll understand exactly what happens when you run a simple hello world program. So let's jump right in. At your screen, you can see three things. Towards your left, we have a very simple Hello World program, and we'll use this particular program for today's explanation. I'll also use this command line prompt to show how exactly operating system calls multiple system calls to make sure it executes properly. Towards the right, this is how a memory layout looks like when a binary program is loaded and executed. And this is from this amazing book called Practical Binary Analysis. And today I'll try to explain the concept mentioned in the book with a practical example. So when you execute a program on Linux, the operating system performs several key tasks to ensure the program runs correctly. Today we'll break down this using these diagrams. Step one is basically loader and the virtual memory setup. So basically, loader is a component of the operating system kernel, and this is where the loader lies in your memory layout. The first job of the loader is to allocate a virtual address space, as you can see in this diagram, which isolates from other programs. So basically, every process have its own virtual space, and then it sets up a memory for the stack, then the heap, then the data and the code section. So this whole virtual address space setup job is the first task of the kernel based loader. The code section contains machine instruction that the program will execute. The data section hold initialized global and static variables. The heap is used for dynamic memory allocation, and depending on the need, the heap memory can be extended or shrunk by different system calls. And then the stack is where local variables, function call, and return addresses are stored during the execution. The loader ensures that each of these sections is mapped to the correct locations in memory before moving to the next step. Second step is loading the interpreter. So interpreter is nothing but the dynamic linker. Its job is to load all the dynamic libraries which are actually required by the binary. So the loader looks for the special section in the binary called inter, and this is the section which specify where the dynamic linker or interpreter to use. So for example, let's see we have our hello world program. So first what we'll do, we use GCC to compile this hello.c to create this hello binary, and we'll run this hello binary and it will nothing but just printing the hello world. When we inspect this hello binary with this utility called file, we came to know that, okay, it's a 64 ELF binaries. It is dynamically linked. That means it required multiple dynamic libraries, as well as it also mentioned this interpreter. So this is the dynamic linker or interpreter this binary is going to use. Other than that, there is also another section, separate section called um, dot interp, which basically contains the interpreter information for this particular hello binary. And as you can see, there is this path information of the interpreter. So in our example, the loader will load this interpreter at this particular lib64 folder, and then the loader maps the interpreter into the memory. This memory mapped area is where loader map the interpreter for more specifically this one. And then the loader transfer the execution to the interpreter itself. The loader's job is done here and the interpreter takes over. Now the major job of the interpreter is to load and link dynamic libraries, such as there are many libraries like libc.so and other. And how do we know what are the dynamic libraries are needed by this binary? We can use this command line utility called LDD, and then we can feed our binary to know what are the libraries this binary actually needs. So hello basically uses this printf function, and printf is coming from libc.so, and that is what the binary dynamic libraries our binary need. So once interpreter takes control, the first task of it is to load the dynamic libraries into this memory mapped area depending on what are the libraries needed by the binary itself. However, to do that, there is a optimization technique which dynamic linker use. It's called lazy binding. So instead of resolving all reference at load time, the interpreter defers this until the function is first called. For example, printf isn't resolved until it's actually needed. We'll cover this lazy binding in more detail in the next video. But for now, just know that depending on which is getting called for the first time, the interpreter will load the dynamic libraries into this particular memory mapped area. Now, the first task of the interpreter is done. Once the dynamic libraries are loaded, the next task of the interpreter is to do some kind of initialization or relocations. So there will be variable maybe in data section or code section which are needed to access this memory mapped area for accessing the dynamic libraries. Those relocations or address need to be remapped with whatever virtual memory address we have loaded our dynamic libraries in. So that is the second most important task of the interpreter, to do the relocation. Now, once the relocations are done, then the third point in the third task is interpreter will identify the entry point of the program, which is nothing but the main function, and then it will transfer the controls to the main function, and then the printf hello world can be run. Um, so just for a recap, in the first step, the loader will load or initialize this virtual memory process layout. It initialize stack, heap, data, code address, the memory, and then it loads the interpreter. The interpreter takes control. It loads the library. It does some kind of relocations and initialization, and then jump to the entry point. That is the main of the function. Now let's use this utility called strace to trace the system calls made by our program during execution. This will give us a detailed look at each step the OS perform to load and execute this binding. So for that, we'll simply call this strace command line utility, and we will feed our hello binary. As you can see, there are so many things happening just to load and execute this binary. It's a lot. So we'll follow one step at a time. So first thing to understand or to observe is this starting execution pointer. So execve is basically a system call which fork another process, or which tries to create another process or another process virtual memory. Once that forking is done, then it call this system call break, which is actually used to get some more memory for the heap or the stack. And then it does more setup information. It map that memory, whatever it has got, and then start the loading of the interpreter. Before loading on the interpreter, the loader reads about reads this file called etc ld.so.preload to understand what are the prerequisite of before loading the interpreter or dynamic linker. Then it also read this ld-so.cache, which is basically cached address of those dynamic loading libraries. Once that is done, then the loader map this interpreter to this memory mapped area, and then it performs some kind of other read information just to make sure it has the proper execution privileges, etc., etc. So far what we have done, we have the loader, then we have initialized some memory, and then we understand what kind of dynamic linker or interpreter is actually needed, and then we will next load this. If you observe very closely, then yeah, just the next line. This is where we actually, this is our interpreter, right? So this interpreter is actually loaded into the system. And once that is done, then the interpreter needs to load the standard library. And that is actually done by next few mmap. So this few mmaps is actually used to load all the dynamic libraries needed to be read. Once that is done, the second task of the interpreter is to do relocation as well as some initialization. We don't have much relocations here, so we'll simply move to initialization. You can see this is where the actual initialization process is getting done. This initialization process is just to support the thread local storage. And then once that is done, then we have some security information. Just say, for example, we randomly generate some number to make sure it's consistent with this particular process. And then we transfer, not we, the interpreter transfer the control to the main function, and then we call the or write the actual hello world on the command line, and then we exit with 0 as a code. To summarize, in this video, we explored how binaries are loaded and executed on Linux machine, more specifically ELF binaries. We discussed the loader, interpreter, virtual memory layout, and analyze system call using strace. If you find this helpful, please like, share, and subscribe. Thank you for watching, and I'll see you in the next video. Thank you.